Okay, we're going to take that example that we worked on before with just finding the shear stress and the normal stress in an arbitrary plane, and now we're going to use the same state of stress and find the maximum shear stresses and find the plane that it's on and how it's all oriented. So let's go back. Here's our state of stress that we've got here. So let's define our basic stresses first. We've done this before, but we're just going to do it again, right? So here's our x plane. So there's our normal stress associated with the x direction. It's in compression, so that'd be sigma x equals a minus 1400, of course, psi. Our normal stress in the y plane is a positive 1000 psi, and our shear stress on those planes is the opposite of the positive sign convention, so therefore it is a minus 500 psi. Go back to the sign convention video to understand what those, to review what those positive signs are. Right? So we got to do this first. Now we're trying to find tau max, which does mean we can go straight to the expressions that we've been provided for those. Right, so I have to look this one up too, sort of, right? Tau max is going to be equal to the square root of something. That something turns out to be the difference between the normal stresses divided by 2, but squared, plus the shear stress squared. Right, now, something very interesting here to take note of. This looks exactly like the Pythagorean theorem. Some sort of hypotenuse equals the square root of the sum of two things squared. And indeed, that will actually be a part of the basis for more circle application for finding these things, which ultimately is actually way easier than working through all these equations, it turns out. Right, so you now just put all of those values directly, including the signs, right? Those got to get in there correctly too. You know, for the shear stress, it won't matter so much because that negative sign was going to get squared, right? So you could be sloppy on that one, but you can't be sloppy here. This is sigma x is a minus 1400 minus the positive 1000. So that's a net of negative 2400 in the numerator divided by 2, so a negative 1200. Ooh, a 1200, a 500, a 12, and a 5. That's that perfect triangle, 5, 12, 13. And so this answer is going to turn out to be, put it in your calculator, prove it to yourself, that that's going to be 1300 psi for that maximum value, right? So that's that part of it. Now, the next part is to figure out how things are properly oriented in all of this. So we can't find the other stresses until we first find out what the orientation of the plane is that this maximum is happening on. So that's what we'll do next. We'll find that plane that the maximum shear stress is, that theta s, right? So their tangent of 2 theta s, right, is going to be equal to, and it's going to involve these terms again, a negative sigma x minus sigma y quantity over 2. That's this quantity right here, but with the minus sign over this one, tau x, y, right? Opposite over adjacent. So in a sense, an analogy sense, what we've got is sigma x minus sigma y over 2 there, and a tau xy over here. And so our 2 theta s is sitting there. There is a minus sign in front of all that. So really, you flip that the other way around and you get it going downwards kind of thing, right? That's coming from our calculus where we got all that. And we substitute that in, solve for first the arc tangent here, 2 theta s, and then when we divide through, we'll find out that theta s is equal to a negative 33.09, I believe, or 33.69 degrees. All right, now remember, in our stress transformation equations and model, everything's measured from the x-axis, the positive direction, with counterclockwise being the positive direction. So this orientation of this plane is such that it starts here and has to then rotate a negative 33.69. So the plane was vertical, then it becomes rotated over, and so it looks like that. And I'll go ahead and put that initial, wait a minute, you said from the horizontal x. Yeah, the x outward normal is horizontal, but the plane it represents is vertical. So when we rotate it, we're rotating both the normal and the plane. So the 33.69 is going like that. Now, the next part, and there's your theta s right there. Now this next part's really kind of wild. Now that we know this value of 33.69 negative, we put it into the stress transformation equation and find out what the normal stress is on this plane. You'll find out that it's compression and it's 200 psi. And if you put that same angle in to the basic TAW, or shear stress transformation equation, you'll find out that our shear stress there of the 1300 is going to be in that direction on that side. Of course, on the opposite side, those two will look like that. You're like, what? So here's what you need to do. You need to go back and study all those equations, put in your values, 33.69, put those in to your sigma equation. And you'll get that that's what's going on when you follow through. Right-hand rule, right, get it into the right orientation, and we end up, it turns out that that's going to be a negative value coming out of that equation, which means you got to flip it, and that's how you'll get it down there. That's one way to do it. The quicker, way quicker, easier way is to use Moore's circle to get this and get the directions. Moore's circle? Yeah, Moore's circle. That'll take a little bit to learn, and that's a wild, wacky thing. But that'll be one of those tools that once you learn it, these things are really super fast to do. They're slow when you have to do it through manipulating the equations. You can get it all right, but the interpretation is difficult, and etc. More circle, once you learn that, really quick visual aid. You can actually do a lot more than just a visual aid, but the visual aid portion alone is enough to make this worthwhile and to go do it. So there's your answer here, orientation of that particular plane. It'll turn out that when we go look at the real stress block here and those other 90-degree planes, the way this would look is you'd have equal values for the normal stress on all of those planes, and then the shear stress at 1300 then would pinch this in this kind of fashion. That's your final answer to the whole thing by the time you're done manipulating all of those state of stress equations. It's tedious and long. It's way quicker to use Moore's circle. And that's what we'll learn here very soon.